And we are back. Apple MLX King here to give you some really great news. So last week, Google dropped a bombshell, Gemma 2. It's quite a remarkable model. So in this video, we're going to go through the paper, we're going to implement it from scratch using MLX, and we're going to see if this model is really good for RAG use cases. So let's get started. Alright, let's get started with Gemma 2. This is today's agenda. We are first going to go through the technical report that DeepMind released about Gemma 2. Second, we are going to implement Gemma 2 from scratch using MLX so that we can run it locally in our MacBooks. And finally, I'm going to show you a use case of the LangChain MLX integration that I built so that you can actually easily build RAG pipelines that run completely local in your MacBook using MLX and LangChain. So let's get started with it. And first things first, I would like to look into the performance because I heard really great things about this model. So let's check it out. Here we are. So there are two things that are quite interesting here. The first one is that Gemma 2 uses significantly less data than Llama 3. And the second one is that Gemma 2 27B outperforms a model 2.5 times its size whilst using less data. That's quite an interesting take. And on top of that, it manages to even outperform Grok 1, which is a model many times over its size. Moving on, Gemma 2 27B, with that remarkable performance, is now the #1 open source model. And this is a chart from LMSys benchmark, which shows that Gemma 2 is ahead of GPT-4, models like Qwen 72B, Command R Plus, which is a Cohere's open weights model, and also NVIDIA's open weights model, Nematron 340B, and of course, Llama 370B as we discussed. So this is quite impressive. We now have pretty much a new open source king. Let's go a little bit deeper. So there's this guy on Twitter that showcased a very interesting use case, which is coding. We know that nowadays a lot of developers are using AI assisted tools, and this is where Gemma 2 27B also shines. And this case in particular is writing Go and Java code. We can clearly see that Gemma 2 27B is close to GPT-4o, Claude 3.5 Sonnet, and ahead of Gemini 1.5 Flash, Llama 370B, and Claude 3 Haiku and Gemini 1.5 Pro. So it's actually up there in the realm of the big API models. So you should try it out for coding as well and let me know how it goes for you. Let's move on into the paper. So this is the technical report released by DeepMind, where they actually introduced these models. As we can just go over it real quick here. We introduced Gemma 2, a new addition to the Gemma family of lightweight state-of-the-art open models, ranging from 2 billion to 27 billion. And of course, now in this particular paper, they are making available the 9 billion version and the 27 billion version. And they will release the 2 billion version later on. So what is quite interesting here, they say right here, the resulting models deliver the best performance for their size, even offer competitive alternatives to models 2 to 3 times bigger. That's just kind of the introduction. So let's look into this part here. I kind of snipped this out because it's quite interesting to me. So they say here, small scale models have also shown a rapid increase in performance, but these gains are largely derived from increasing length of training. So this is an interesting take. So they are actually going against what Meta did with Llama 3, where they did a longer training run, and that way they kind of improved performance without changing the model architecture whatsoever. They say this approach only scales logarithmically with the data size. And the latest small models require up to 15 trillion tokens to improve state of the art by less than 1 to 2%. So that's a heavy blow, right? And they say yet these continued improvements provide evidence that small models are still undertrained. Okay. In this work, we'll explore alternatives to improve small model performance without solely increasing training length. One solution is to improve the quality of information received by the network at each training step by replacing the next token prediction with a richer objective. Okay, I'm convinced. Let's look into what you guys did. All right, so let's look into the model architecture. This is a very interesting one. We can see here they have a 2.6 billion parameter model, 9 billion and 27 billion. In terms of the dimensionality of the model, it does increase, it changes slightly. Number of layers, of course. So the first one has 26, 42, and 46. All of them have pre and post normalization. So this is a very interesting approach they took here. This does help stabilize training. So it's something I've been seeing more and more with new models that I add to MLX. A lot of these new models are adding extra normalization to stabilize training. And in terms of nonlinearity, they still remain with Gigelu. Feed forward dimension, okay, nothing too crazy. They all used grouped query attention. If you don't know what grouped query attention, check out my Coding Llama 2 from scratch series. I detail and I even code grouped query attention from scratch and show you how it works in detail there. So the high level idea of group query attention is that you have a single key and value, right, that share multiple queries, so n queries. So it could be 6 query heads per key and value, and you can kind of expand that to however many groups you form. And of course, if you want deeper details, check out my video and you'll see everything there in code and with the paper with the illustration. On top of that, we can see here we have 8 heads and 4 keys and values. So as I was mentioning earlier, you will have 8 query heads, right, that are gonna share 4 key and value heads. So probably it's gonna be like a 2 per 1 ratio. And then on the 9 billion, you'll have 16 for 8, 32 for 16. And they will all share. And for the big one, you have 32 to 16. Finally, we'll have the head size. It actually goes down with a bigger model. That's quite interesting. I would like to know why they do this. And your global attention span, which is going to be your context window, it's 8,000. And with a sliding window of 4,900. So this actually does help. I think if I remember correctly, they interleave this sliding window attentions throughout the model. Finally, they have the vocab size is the same, 250,000. And they all tie the embedding. So basically, they tie the embedding matrix with the prediction head. All right. So here we have kind of the parameter count, embedding parameters, how many they have, and non-embedding parameters, meaning your attentions and linear layers and so on. Let's move into training data. This is where one of the interesting parts that I mentioned earlier is. So they say we trained Gemma 2 27B with 13 trillion tokens of primarily English data. All right. So that's already 2 trillion tokens less than Llama 3. Then they say we trained the 9 billion model with 8 trillion tokens. We are talking close to half of the tokens used to train Llama 3. And the last one, which is 2.7 billion, they use a tiny fraction, which is around 2 trillion tokens. And they say these tokens come from a variety of data sources like web documents, code, science articles, and so on. They say our models are not multimodal and are not trained specifically for state-of-the-art multilingual capabilities. So they are actually stating that, hey, if you use this for multilingual use cases, you might actually have bad performance, or you might need to fine-tune it to be able to unlock those capabilities. Then they say the final data mixture was determined through a series of ablations similar to the approach of Gemini 1. And they do mention that later in the paper. Then they have the tokenizer. They're using the same tokenizer as Gemma 1 and Gemini, which is a sentence-piece tokenizer with split digits and 256,000 entries, which we saw earlier. Let's move on from there and go into stabilization techniques. So here's where they mention why they're using the pre and post normalization. They say to stabilize the training, they use root mean squared normalization to normalize the input and output of each transformer sublayer, the attention layer, and the feed forward layer. So that's pretty good. I've seen this more with the attention layer, where you'll see this same normalization done to the queries and keys or keys and values as well. And finally, they do also mention here logit soft capping. So they say we cap the logits in each attention layer and the final layer, right? Such that the values of the logits stay between minus soft cap and plus soft cap. More specifically, this is the implementation. So you have the soft cap value here. You have your logits. You divide them by your soft cap, right? You apply 10 and then you multiply with the soft cap. And then those will be the logits that you pass on to another step. So this is pretty straightforward to implement, and we're gonna see this in a minute when we start working with the MLX code. Now, they also mention knowledge distillation. So the idea of knowledge distillation is that you want to compress the knowledge of the big model into a much smaller model. How do you do that? You run your data set, your training data set in this case, through both the teacher model, which in this case was Gemma 2 27B, and you also run it through the untrained small model, which is Gemma 2 9 billion. They output their logits, meaning their kind of predictions there, and you calculate the loss difference between the output response of the teacher and the student, and you use that to improve the student. So as training progresses, this student model will learn how to make predictions or provide responses like the teacher model. So that's a high-level overview. You can look here in this paper where they talk about response-based knowledge distillation and even feature-based, which instead of calculating the loss on the logits, you also calculate the loss on the activations, which is also quite interesting. Now, with that out of the way, let's go into the most awaited part, which is implementing this into MLX. So what do we need to do here? First, we need the paper or source code. Second, we need the model weights, right? And finally, we just need to implement it. We already have the paper. We can look at source code options if they already exist. In this case, I always try to find it in transformers. They always kind of have some implementation in there or a PR. So if you don't find it directly here, you can just check the PRs. In this case, they already merged it. It's the Gemma 2 modeling Gemma 2 file under the Gemma folder under models. And here we have pretty much everything we need. And I will go through this in a minute. So this is all the code. And don't feel intimidated if you see a lot of this code. This is specific to transformers. When we actually implement this, the code will be much leaner and smaller because we don't have those dependencies. And they do have a Gemma specific repo. So this is Google's implementation of Gemma 2 or the Gemma family of models using PyTorch. And you can see here, it's only about 700 lines of code, but I think in MLX we can do better. So let's get started. Now let's move on to the second phase. The easiest and fastest way that I know of acquiring model weights is going to the Hugging Face hub. In this case in particular, this is a Google's release, so you can find it under the Gemma 2 release collection. In this collection, you can find model weights for variety of libraries. The first one are transformer specific, the second one are PyTorch specific, and the last set is for Keras. Now, the one we want is the transformer specific weights. In this case, we want to download the Gemma 2 9 billion parameter instruct version. To do that, you can just open up the model weights. There are myriad of ways you can go about this. You can clone the repository, right? But I personally prefer to just download it using transformers, using this command here. Once you have the model weights, you can find them in your directory by going into your terminal and going into the cache directory, and you'll find the hub. And here you can see that I already downloaded these models previously. So the model weights are on my machine. I don't have to re-download them when I'm running. Now that we have the model weights, the first thing I like to do is to check the configuration file. This gives us information about this model. So this is where we find the entire configuration, the same we saw in the paper, but with a bit more details. For example, the activation in a specific name here. You have the model type, right? This also helps. If you want to know whether, for example, MLX already supports a model, by checking the model type, you'll be able to know if it already exists, because we use the same naming in MLX as you find here in this configuration file. Then we have here pretty much the entire configuration of the model and the architecture as well. So good. I already seen what I want here, and I already have the model weights. Moving on from here, I just need to go to my IDE. But before I do that, I need to clone the repository for MLX. In this case, you need to come to ML Explore, MLX examples repo. Within this repo, you'll be able to clone it. You can clone it in any means you want via the CLI or HTTPS. Once you clone it, you will have something like this in your IDE, right? You'll have this repository. I want you to open the LLMs folder. Within that LLMs folder, you'll open again an mlx_lm folder. This is the MLX language model library where you'll be able to find all the models. So there's a models folder there. Within that models folder, you'll find all the models that MLX currently supports. In this case, I have the Gemma 2 file empty, but if you download this with the latest release, this file will be pre-filled with the code. In this case, I want to show you how you would go about converting a transformers model into MLX format. So that's why this is empty. We already have the Gemma, the first Gemma model is already here, and the format is quite similar. We have a data class, and then we just define the classes that we want, for example, for attention, RMS norm, and so on and so forth. But we will do all of this in a minute. Okay, we now have this file here, and we want to start converting. So what do we do first? We can check the reference implementation for the first steps. We can come here. We are using the transformers implementation. I know it might look daunting, but we can just look at their implementation. I know it might look daunting, but we just look at their implementation and we can find the relevant information. And I know it looks daunting, but we just need to kind of follow their guidelines. I know it looks daunting, but we're just using it for inspiration to know what exactly we will be doing. In this case here, we have the RMS norm. It's very straightforward. But before that, let's just get started here. Initially, we are just going to import a data class so that we can create the configuration for the Gemma family of models. And let's go. So from data classes, import data class. That's what we want initially. So we are going to create a data class, and then we are going to create a class here called model args, right? And this class is gonna have the same format as our configuration. So if we go back and we put this side by side, it will be much easier. Let's just close this and open our configuration file so that we can see what we are going to be doing. Or we probably prefer the other way around. All right, this is much better. All right, so attention bias, we do need that. So attention bias, and this is a bool, so equals to false. We don't need the attention dropout, but we do need the attention logit soft capping as described in the paper. So this is the value that we're gonna use to normalize our logits in our attention. So logit soft capping. This is a float equals to 50.0. Cool. We don't need this token ID. We don't need all of this. We do need the final logit soft capping. So this is applied after we make our predictions. So logit soft capping. Okay. Yep. All right. So this is also a float equals to 30.0. Then we do have the head dimension. We do need that. Head dimension. This is just an integer of 256. We don't need the activations. We already know they're identical, so we'll just kind of hard code those. Hidden size, we do need. This is an integer of 3,584. We don't need the initialize a range because this is kind of just initialized from the pre-trained weights. Intermediate size, let's take that. We do need that. Intermediate size. This is for our MLP layer. This is an integer, 14,306. Okay. Max positions, we don't need that at the moment. Because our rope in MLX already kind of does this under the hood. Model type, we do need model type, and this is a string, and we can just, all right, number of attention heads, yes, number of attention heads. This is a integer of 16. Number of hidden layers, this is an integer of 42. And then we have the number of keys and values. Yes, that's important. The key value heads. This is 8. All right. We don't need the token pad ID. We do need the query pre-attention scalar. Okay. This is an integer of 224. RMS norm epsilon, that's important. We do need this value. This is a float. of 1e neg 606. Okay, rope theta. This is the value that we're gonna use in our rope. So this is a float of 10,000. Okay, I wonder if this scaling this value would also increase the context size as well. For this particular model, I noticed that other models work that way. I don't know how this one in particular would react. So this one here is integer of 4096. We actually don't need this values here because we are not going to be using this sliding attention. It will work without it. Transformers version we don't need. We do need the vocab size. All right. So now that we have that, this should be just an integer of 256,000. Cool. Now that we have that, let's move on into implementing other things. Let's import MLX for starters. Import MLX core as MX. Import mlx-lm as nn. So MLX has a similar interface as PyTorch or Keras if you are used to those, but more so PyTorch. I feel like it's more closely related to PyTorch in terms of API, and I like it for that particular reason because I'm really well versed with PyTorch. Now that we have that, let's move on into implementing other things. MLX does have a class in base. I think we can separate these two pages now so that we can clearly see. All right. MLX does have this class here, base model arguments, that has a method that helps you load your configuration from a dictionary. If you notice, our configuration file is actually a dictionary, so this kind of makes it easier. So let's import this before we go on and make our class inherit from that. So we just say from .base import base model args, and now our model args already has that method. Moving on, first things first here is that we're going to implement the RMS norm in MLX. So let's get started. So class RMS norm, this is going to import from NNN module, just like in PyTorch. Here we are going to initialize it. Init. There we go. This is going to take the dimension and epsilon. And we can actually hard code an epsilon here, which is going to be 1e neg 5. All right, now that we have that, let's move on into actually implementing this. So first we need to create the weight matrix, which is going to receive the weights from the pre-trained file. So first we need to initialize the weight matrix, which is going to kind of load the pre-trained weights for the RMS norm layer. So we're going to say weight. This is going to be an MX of ones, and it's going to have dims or dim. So this is just basically a vector. Now we do have to initialize the epsilon that we're going to use later as well. So eps is going to take the value we designed. Now, the difference between MLX and PyTorch is that PyTorch uses forward and MLX uses call. So we're going to use call here, but it doesn't differ as much. So self, and then here we take x. X is going to be an MX array. And this is going to output an mx array as well. Now that that is done, let's implement it. So return mx fast RMS norm, and then RMX norm x 1.0 plus self weight self dot epsilon, and we are going to give this the same type as x because it's one of the requirements in the paper. They kind of upscale it again or scale it to the initial input. This fast.rms norm, it doesn't mean that you cannot implement your own logic. You can, but MLX already has this, and this is running using C, so it's going to be much faster than the Python implementation. It's just a nice speed gain that you will have there. Okay, cool. So we already implemented all of this, right? In just a few lines of code. Moving on, and as you can see here, that's exactly the same thing as they do in their implementation. Cool. Rotary embeddings we can skip because we already have the rope implemented in C as well for MLX. Let's move on into the MLP layer. So we can see here that it has a gate projection, up projection, and down projection with an activation. That activation, we already know that is a GELU activation. So let's implement this. Class Gemma 2 MLP, and then this is also an NN module. There we go. We're going to initialize this init. This takes a dimension and in hidden size. Okay. Let's see. Yeah, about that. Oh, hidden size and intermediate size. It's okay. So we just call it hidden size and intermediate. Intermediate size. Okay, now that we have those two done, let's start defining our gate. So gate projection, this is going to be an NN linear from hidden size into intermediate size. And the bias here is false for all of them. So actually we can just set, to make it easier, bias false. And then we just pass it on. Then we have a self dot down projection. This is going to be an NN linear from intermediate size to hidden size. And this also takes the same bias, which is false. And we have another gate, which is going to be an up projection gate. This is going to be linear, and we are going to go from hidden size to intermediate size with a bias set to false as well. All right, now that we have that, we can just implement it directly. As you can see here, there's not too much to do. You just go straight into the forward method. They say first you apply the down projection. Actually, first is the gate projection with the activation that is multiplied by the up projection, and then both of those are, or the result of that operation goes into the down projection. Cool. So let's do that, exactly that. So call, and here we are just going to put x. X is going to be an mx array again, and it's going to return an mx array as well. And what we do here is self.down projection. Within that, we have actually and then Jelu, right? And then inside that Jelu, we are actually applying a gate projection x, which is going to be multiplied by self.up projection that is on x. Let's see. This looks good. Perfect. All right. Repeat k and v. We don't need that. MLX actually already has a function that does this built in. Attention. So yeah, we want to implement the attention mechanism here. But we are implementing a group query attention. That is something that we need to keep in mind. So what do we need here from the attention? Let's start implementing. So just the configuration layer ID. I don't think we need the layer ID. What are they using the layer ID for? Let's see. Layer ID. Okay, they're using it for the sliding window, but we're not going to be implementing that, so that's fine. Let's start implementing this. So class attention, and this is also an NN module. And within this, we are going to do def init. So we're going to initialize this, and it's going to take arguments that are actually the model args that we defined earlier. So this way we'll have a nice autocomplete. First, we want the dimensions. These are going to be arg.hidden size. Then we want the number of heads, which is going to be an n underscore heads. And we can also pass it on here as a variable to use it later when we're creating the linear layers. And here this takes from args, and we can now just use our autocomplete self dot now and kv heads, and we could do the same here, kv heads and heads. Okay, and this takes from our num key heads. All right, now we're going to see how many times this repeats. So because we are doing group query attention, we will have less number of heads, KV heads than heads, and we want to know how many times we want to copy the keys and values so that we can match with the number of heads and be able to make the attention, be able to create the attention matrix. All right. So this is going to be a number of heads divided by number of KV heads. All right. Then we will have the head dimension. And let's just double check that we are on the right way. Yeah. So we are on track. Head dim. Cool. So we're going to have here our head dim. And this is going to be hargs head dim. Cool. We also want the attention logit soft capping. So we're going to say attention logit soft capping. And this is going to be the same as our attention soft capping here. Cool. We need a value to scale our scores or attention scores, and this is going to be just the not self, but args query attention scalar times 0.5. So we'll be able to scale this. Just to double check. Yes, that's exactly. Oh, neg. If we want to, it has to be neg. All right. So, yeah, so we did it correctly. Let's just format it nicely. There we go. Now we go on to create our layers. So we'll have the Q projection layer. This is going to be an linear, right? And this is going to take dimension and it's going to go into n heads. And the bias of this is going to be our attention bias. And we can now copy this multiple times and be able to just change. So the second one is going to be our K projection, and this goes into, instead of n heads, goes into nkv heads. And the same goes for our our V projection. So now we have that. We need something to be able to project this to, which is our out projection layer, which in this case is just going to be oproj projection, and this is going to be an linear layer that does, let's see, number of heads multiplied by head dimension into hidden size. Okay, so it's going to be number of heads multiplied by head dimension, and this is going to go into dimension, and the bias we already know. Yeah, so we have that right. Let's move on into defining our rope. So for this, you're just going to say self.rope and use mlx's internal built-in mechanism, or method. So this takes in dimension. This is not traditional, so let me just add it here. Rope traditional. This is going to be a bool and is set to false. By this model does not use the traditional one. All right, so rope traditional, no. It takes the base, so the base is 10,000, which means base is going to be our args rope theta value. Oh, I need to define this. There we go. We have everything we need, I guess. Let me just check. Yep, after that we just go straight into creating our forward. So let's do this. Instead, we're going to do call. There we go. And here we define a few things. We know that the output is going to be an mx.array for sure. And inputs, we can see that first we have x, which is also an mx array. We have our mask. We do need a mask here. So this is going to be an mx array as well, but should be optional. And then finally we have our cache, which is going to be pretty much a tuple, but a tuple of mx arrays. So something like this. And you can see that by coming into base, and you can tell that this is the KV cache class, and you can see that it returns an mx array of keys and values. Oops, yeah. And we want to define those here. So let's import some typing. I don't want, okay, I want optional, and I want tuple. So let's use those. First, optional. This should be optional and defaults to none. None. And yeah, we need to indent this. Okay. All right. So here we do have a optional that goes into a tuple, and this also defaults to none. And it should work. Okay, so not really curly braces, but straight. Okay, cool. All right, so let's start implementing. First, let's get the shapes. We're going to use that to format our tensors later. This is the shape of our input mx array, so this is just going to be shape. Now that we have that, let's create our queries, keys, and values. And to do that, we just say self.q proj, and this is just going to be x. And this is going to be self.kproj x. And finally, our values self.vproj, and then x. All right, we have those. We can now format these tensors or arrays, in this case mlx arrays, into the shape we need them to be. In this case, it's going to be queries into queries dot reshape, and we want this to be a batch size by self dot n heads. Actually, we have the length earlier, so length, and the last part we don't need, it can just adjust on its own. And after that, we want to transpose this into a 0.1.3. So we're going to move these two positions there. And we are going to have our keys, and our keys are just going to be a reshape of B, same L, and then instead of n heads, we're going to do kv heads. And -1 transpose into 0 2 1 3. Since the last one is similar as this one, we just copy paste and just change a couple of things. And we just change this to values and values. All right, so let's move on. We now have to implement the cache logic. So if cache is not none, here we're going to have queries, and our queries, when we do rope, are going to, of course, take the queries here, and then we are going to offset by the cache offset that we already get from the kv cache implementation. Offset. And to verify this, you could just come here and see that you actually do get an offset value when you are creating your KV cache, or as you update it. We're going to do the same thing for our keys. It's going to be self.rope keys cache offset in this case. then cache dot offset. Cool. Now that we have that, let's move on into updating this. So it's going to be keys, values, and we are going to say cache and use the update and update and fetch. Yeah, so this one here. So update and fetch, it takes initially keys and also takes the values. So we now updated our cache. And if this is not there, we are just going to update our rope values. So rope for queries without any offset and keys without any offset as well. All right. Okay, so we have that done. We can move on to the next part, which is pretty much the scaled dot product attention calculations. And the way we start that is just by scaling the queries. And we can just scale with the scale value we have up there, self.scale. Then we go into pretty much, we now have keys and values that are less than our queries, so you won't be able to do the scale.product attention because the shapes will be all wrong. So the way we can do this is by just taking the existing keys and values and copying them to be able to match the queries shape, and this way we'll be able to calculate the attention scores. This is kind of the premise of grouped query attention. So we do that by just saying self.repeat is bigger than 1. If you have to repeat, we are just going to say keys equals to mx repeat, and then here we say keys and then self.repeats, right? And we choose the axes. The axis we want to repeat, this is 1, right? And it's the same exact thing for values. Values, so self.repeats, axes 1. So this is gonna help us match the dimensions and be able to multiply. So now we can just go ahead and do the dot product, calculate the dot product scores. So this is just gonna be queries, and here we need to transpose this. In PyTorch you could do something like that, or NumPy you could do something like that, but here we're going to do transpose. We are going to take 0, 1, and transpose just the last 2 dimensions. This way we'll be able to multiply these, and after that we are going to add the soft capping. So we now have the scores. We do need to do the soft capping. It's something we can check here. So after they calculate, so after they calculate the scores, right, they do scaling afterwards, it's fine. I think we could do the same as well. It's not really a big deal. After they do that, they calculate the attention soft logits before continuing. So let's do exactly that. We can move this operation, I guess, here. Let's see what they did here. Yes, so to make sure that it works well, we're just going to first calculate this and then do that. Okay, so here we have the logits are going to be equal to logits, not really, so soft cap times, or yeah, soft cap times your tan h over your logits divided by soft cap. So the way we can do that is by just saying, let's see what they did here. Attention weights are gonna be equal to the division, then applying the torch, the 10, and then multiplying. So we could say scores equal to mx 10 age. Of course, we already know that this is gonna go in there. So we say scores divided by self dot attention of G capping, and then scores are gonna multiply equal to self dot attention dot dot. So now that we have that, we can move on. We can go into if mask is none, or even better way is if the mask is not none, this is if the mask is not none, scores are plus equals the mask. We add that in. And finally, we are going to calculate the softmax of these scores. Softmax, softmax, and let's see. Okay, softmax on the dimension -1. Okay, upcast the attention to float 32. Then get it back to the query states. Range, okay, cool. So the way we can do that is just by saying scores as type mx float 32. And you can check this actually by going into the mlx docs. Let me open it again, mlx documentation, and you can search here data types, and the first hit you'll see the list of data types they have, and you can see that float 32 is here and is a part of core, so you can just get it straight away. All right, let's move back here. And after that, they add a dropout, but we're not adding dropout since we're running inference. And then after that, they do the math move between the attention weights and the values. Okay, so we do that first. This is going to be on axes instead of dimension. We do axes in MLX. And this is going to be as type scores D type. All right, now that we have that, we can say output is going to be scores at values. And finally, we are going to have the output has to be transposed or reshaped first. So reshape into BL -1. So we want it to the last dimension to be a single, like adjusted automatically. And actually we need to transpose the dimensions as well so that it will fit on the next one. Transpose, this is going to be 0, 2, 1, 3. And there we go. So oproj is going to equals to output. So this is our attention. It's kind of pretty much identical. So this is what we were doing, transposing and then reshaping into batch size, length, and then -1, then passing it down to the O projection. Okay, now that we have that, we don't need flash attention. Actually, Gemma 2, because of the attention soft logits, does not work with flash attention or SPDA attention, so we can skip those. Now we go into building the decoder. So let's do exactly that. First, we need the self attention. This is going to take the attention we created, MLP, we have 1, 2, 3, 4 layer normalizations or layer norms. Okay, so that's all we need to initialize this. So class Gemma 2 to decoder layer, and then module, and then here we're just going to initialize it. And this takes an arg, which is going to be a model args. So self dot args is going to be args. We will need it later. Self dot hidden size. This is going to be needed to create. Yeah, so this is going to be needed to create our layer normalizations. So this is going to be hidden size, self dot attention, which is going to be self attention in this case again. This is our attention that we just created, and we just need to pass it args. And we now have our MLP, self.mlp. This is going to be Gemma to MLP, and we're going to pass it we can do this to make it easier, hidden size. So this is going to be our hidden size. And we are going to need our intermediate size as well. So we can just put it up here. Self dot intermediate size is equals to intermediate size intermediate size. There we go. So we're going to pass that here. So we have our MLP, and now let's initialize the layer norms. The first one is input layer norm. Okay. So dot input layer norm, and this is going to be our RMS norm. It's going to take our hidden size, and it's going to take our epsilon. And we are going to create others just like this. So the second one is going to be self dot post attention layer norm, and we are going to have our self dot pre forward layer norm, and another one which is going to be post forward feed forward layer norm. Oops. So there we go. And this is actually supposed to be feed forward. Now that we have those in place, let's create our logic. This takes in X as a MX array, and besides that, it takes the mask and the cache. Mask, this is going to be optional. MX array. And then we have our cache, optional, mx array as well, but it's supposed to be a tuple, so let's make that a tuple of 2 mx arrays. And this is also none. And within here, we just have to define our logic. Oh, it outputs an mx array. So, all right. So what is our logic? We can look here for guidance of what we are going to do. We take the residuals and put them in from your hidden states. So we can say R is going to be X, but we don't really need to do that. So we can say first our hidden state, or R, let's start with R. It's going to be input layer and then self attention. Okay. So self attention, it's going to equal into self input, not input, is it input layer norm? Yes, input layer norm X. I guess we did first part correctly, so input layer norm, then this, and then we have another one which is going to be post layer attention. So we have R equals to self dot post attention. Finally, we have here, instead of R, we can just say age is going to be plus these two, right? And from there, we can say R is going to be equals to self MLP, and MLP is going to be self dot pre feed forward. And actually, this is not X, this is R. And here, this is going to be H. And after that, we are going to say H plus self dot post feed forward, and this is going to be R. And we have it running, up and running. Cool. So this should work. Yeah, hidden states, and the hidden states are basically post, and post is mixing in with the residuals that are kind of here. So yeah, it should work. It's just a bit more compact and better represented. Another thing, what are we missing? Okay, so these are not being used. Oh, our attention takes in a mask and takes in cache. So yay, we have that working. Let's move on. We have the decoder implemented, so we can just collapse it. We don't need this, we don't need this, we don't need this. The model. So Gemma 2 model is going to create the embedding layer, the layers, and then normalization. Okay, let's do that. So class Gemma 2 model, and then module. So let's initialize this. And here we're going to take args, and this is going to be, of course, using our class up there. Then self.args. And what we need here, we do need the vocab size now that we are defining our embedding matrix. So vocab size, this is equals to args dot vocab size. And we also need number of layers, so self number of layers. This is going to be args hidden layers. Okay, we use the same nomenclature, so hidden layers. Now that, can we just define that we can assert that if vocab size is bigger than 0. So now we can create our embeddings. This is going to be embed tokens according to the weights, and then we are going to do an embedding matrix, and this takes in a vocab size times hidden size. So let's just do this in a nicer way. Vocab size, and we also need self dot hidden size. Args hidden size. So there we go. Yeah, we got it. And we can now create the layers. So the layers are pretty simple. Instead of module list in MLX, you just can create a list and then just define the module you want to iteratively create or dynamically create. Here, we're just going to say for underscore in range num hidden layers. There we go. And finally, we do have another normalization layer here. It's going to be RMS norm, hidden size, and args dot RMS. There we go. Let's move on into creating the forward for this. This is going to take inputs as mx arrays as well, and it's going to take in cache as pretty much optional tuple of mx arrays. So let's move on. Okay, so now that we have that created and out of the way, this is going to return an mx array. And here we can add the logic. So the logic is very simple. We have a hidden state. This is going to create some embeddings. So we're going to do that by doing embed tokens on inputs. And after that, Gemma models in particular have another scaling factor right after the embedding matrix. Without this, it will not give you the results you want. So you might want to consider checking if you're having any bugs here. So you do X or H in this case, you multiply it by the factor, which is going to be self.args, hidden size by 0.5. So that's all you need. Other models don't really use this, but Gemma in particular uses it. Now let's move on. Mask is going to be none because we haven't passed any up to here. And we're going to create it dynamically. So we're going to say if h shape of 1 is bigger than 1, we want to create it. And we say mask is equals to, and then multi-headed attention, create additive mask, and we pass in that particular shape that we have in our hidden state at the moment. Then we are going to just change the data type of this mask, so S type into age D type. And that's about all we need. Then we can pre-fill our cache. So if we don't have anything in our cache, we want to pre-fill it. And the way we do that is just by saying cache equals to none, and we multiply this by the length of the number of layers. So layers. And finally, we just do layer and cache in zip. So we zip the layers, soft layers and cache, and then we just going to pass this through the different layers. We say age is going to be equal to your layer, and the first thing it takes its age, and then it takes the mask, so age, mask, and C. And after that, we will do an input normalization, which is just gonna be norm on H. And that's about all we need to implement this part here, right here. So we embed the tokens, right? We create or prefill our cache. Same thing here with our mask. We also normalize, right? So this is something that you can see here. So Gemma downcast the value below float 16, which causes this error. So you have to normalize it. And we just pass it through the layers. And after we pass it to the layers, we normalize and provide the output. That's it. So we can now, okay, collapse that. And finally, we have our Gemma for casual. So Gemma for casual is going to have a model, vocab, size, LM head. So let's create that. And it just takes the configuration. So here we're just going to define class model. This is going to be an NN module. And this module, we are going to define an init. Within this init, self.args. We're just going to take our model arguments, right? And we are going to start defining what we want. Super. And first thing we want is the model. Model is going to be Gemma model. It's going to take in the arguments. We do need to keep the arguments here because we're going to use them later as well. And finally, we have the LM head. But if we go back, this model does have tied weights. They mentioned this not in here. Okay, it's not in here, but they do mention in our paper here that they don't. Yeah, so they have the tied embeddings, which means they don't have a separate weight matrix for the prediction head. You'd have to use the weights of the embedding matrix to be able to kind of decode your logits into the kind of output space you want. So the way we can do that is just by not having that layer here and just diving straight into def.call. And we can remove all of this. This only takes first inputs. inputs, which are going to be an mx array, and also takes in cache, which is going to be an optional tuple with an mx array, comma mx array. There we go. And this should output an mx array as well. So how do we go about this? Let's look into it. If we come to the transformers code here in the forward, we see that we don't have a lot. First, we just pass in the inputs into the model. After that, we pass it through the LM head. In this case, we have the weights tied, which means you'll just have to do a dot product here. And finally, we have the soft logic capping. All right, so how do we go about that? Soft.model. So that's going to be out soft.model. And this takes in the inputs as well as the cache. And after that, we are going to do output. The output is going to be output. So then we do the output equals to self.model.embed. Should be embed tokens. Yeah, embed tokens. And this is going to equal our output. And actually we do here as linear. This is what will get us access to pretty much doing the same thing as out at self model embed tokens weight t, perhaps something like this. It should be something like that. So this is what this as linear does. After that, let's apply the soft capping. All right, soft capping. Let's separate these. And the way we do it as before, so out is going to be equals to mx10h into our out divided by self.args.final logit soft capping. Out is going to multiply the logit soft capping self.args.final logit soft capping, and that's how we have our final result. So let's test that out. But before, I just want to check self-embed tokens is the same. So let's check out this code. It's like under 200 lines of code that we just created here. So let's see how this runs. First, I'm just going to clear this and also clear here. And I already downloaded the model weights. So the way you can run this is just by saying Python mlx-lm underscore generate, pass in a model, which is going to be Google /Gemma 2 9b instruct, and we're going to have a prompt which is going to be hi, and we are going to have also max tokens set to 10. But before that, let me just double check one thing by looking into other models. So we do need to define a few properties before that, otherwise MLX might give us an error. So we need the layers, head dimension, and NKV head. So let's implement that. before we move on. So we have a property for def layers, just gonna be our layers of the model. We'll be able to access those easily. So the return self dot model dot layers. Then we have a property for our head dimension. So this is going to be return self dot args head dimension. Then finally property def nkv heads self, and we are going to return self dot args and number of keys and values. There we go. So this should work now. So let's run it by closing this, and let's run our code with this command here. If we run this, we have some errors here. Let's look into this error. What does it say? Model layer self-attention, QProj weight, model layer feed forward, weight, though all of those are missing. So we got an error saying that the weights here and the weights here in the layers don't really line up properly, but mostly in our attention head. So let's look into that and debug it. So let's see what error we got. Attention, yep, here we are. So we said NKV heads. This must not be correct according to the model. Okay, so we were missing multiplying it by the head dimension. So all we need to do here is just say head dimension, and then just kind of spread that out throughout. So we can do self dot head dimension and the same thing here. So these errors are actually quite handy to tell you how your weights are matching to your model. So you can see here received parameters not in the model. And you need to kind of just look into those and see what's wrong. So now if we clear and run the same command as before, we should get an updated error. Let's look through our code and find out the bug. So RMS norm is there. It should work well. This should work as well. What else wouldn't work? Dimension. It's not supposed to be dimension. It's supposed to be head dim. All right. And yeah, everything looks okay. The decoder layer looks okay. We also have the model. Okay, everything here looks fine. Oh, we are calling in the decoder layer, so this must have been an autocomplete error, so we need to actually call the Gemma 2 model. Now, let's clear this and run it again. Okay, it's loading our model weights. Oh, there we go. And now it's running on MLX, and it's running actually quite quickly here on this M3 Max. Let's give it some more tokens. Let's say 50, and let's see what we get. Hi there, okay, cool. This is pretty awesome. Now, this is running in at 18 tokens per second on the prompt and 13 or almost 14 tokens per second in generation. Let's kind of profile this and look at how this looks like. So I would like to use mactop. So sudo mactop print, let me put the password here. There we go. And let's make this a bit bigger so we can see. It's taking around 62 gigabytes now. That is impressive. What else is open here? Nothing else. Nothing else. There's no big model running in the background. So we can clear this and see how much we will get when we run this model. So memory is going up to 70 gigs. So we are talking over 10 gigabytes to run this, close to 20 at full precision. Now we can do something really cool. Since we already have the model source code in MLX, we can quantize this model using MLX's already provided conversion script. So here we just do Python m -m mlx_lm convert, and then we pass in Hugging Face path. This path is going to be the path that we provided earlier. So Google /Gemma 2 9 billion instruct, and then we can just pass -q. This is going to convert this model into 4 bits. You can also do --q bits and set up to 8. So this will quantize it to 8 bits. Let's just do 4. It's going to be much faster, and we'll be able to see the benefits in the lower memory usage. So once we do that, it's going to create, you can see that it's quantizing, but it's going to create a folder called mlx_model. There we go. It's quantizing it. It's going to take just a second. There we go. It's done. So now if we look up here, we will see that we have a new folder called mlx model with the safe tensors, the configuration, and everything we need to run this in MLX much quicker. So all we need to do now is to, instead of passing on, when we are doing the generate, instead of passing in the model repo, we're just going to pass in the name of that folder, which is going to be mlx_model. And now we can see how much quicker it is. It just took like a few gigs, like 2 to 4 gigabytes, and is significantly faster. So prompt tokens, before we were doing 15 tokens per second, now we are doing 43, almost at 3 times speed up. And the same thing for the generation speed, we are doing nearly 3 times as fast. So now at 40 tokens per second, as well as previously we were doing 14. So now all you need to do, if you want to upload this to Hugging Face, you can use the same script. Instead of just finishing here, you add upload repo, and then you can pass in the repo you want. So in my case, it would be Prince Kanuma, and then I can say Gemma 2 9-bit instruct 4-bit MLX, and that's all you need. It's going to quantize it and try to upload this model weights to the Hugging Face hub so that you can share it with other people and also just easily have it available there to download in other machines if you want to. So this is how you get started with running Gemma 2 locally on your MacBook using MLX, and also gain speed advantages by quantizing the model, meaning you use less resources and the inference can be faster. So now it's uploading, and you can see that it's uploading the model weights to my repo. And here's an example. We can follow this link, and if we open this in the browser, you can see that it created in my personal account a new repo with the Gemma 2 instruct 4-bit MLX, and it's now kind of uploading that to my account, and I can re-download it or share it with the community by making it public. But I won't do this right now because I already uploaded the model weights for Gemma 2. You can find them in the MLX community. So if you come to MLX community, and here in the MLX community, you will see that there are a few collections, one of which is Gemma 2, and all of these are models that I uploaded earlier, so you can find just all of them. So I'll cancel this. There we go. We don't really need it anymore. This is all you need to know about MLX to be able to convert any language model and be able to run it on your MacBook and even share with the community that is now growing. We are getting closer to 1,000 models and even more than 1,000 people in the community. So your contributions are more than welcome. So coming back to here, just to summarize, we saw what Gemma 2 is capable of, right? We saw that the performance is actually quite good. We got to inspect the paper, right? Understand how the architecture works and how it's supposed to be coded. Understand the training data and some of the things they did. Then we also implemented it in MLX. From here, there are a couple of things that you can do. You can go ahead and fine tune this model. And for that, my friend Sun on Twitter has created some resources around how he's fine tuning Gemma 2 with some proprietary data. And I'll add the links in the description below, alongside other resources on your journey on how to contribute into MLX and some of the coding examples, including the MLX repo that you can go and check out some of the PRs and the code that is there. And finally, on the next video, I'm going to show you how you can leverage the MLX integration with LangChain to be able to create RAG pipelines that run completely local on your Mac, powered by Gemma 2. Here's a high-level overview of how that would look like, and I'll catch you on the next one. Bye-bye.